So last week we were working on projected at an angle questions. Okay, so what we're going to look at here is this old show from the 80s, well, late 70s, early 80s, called The Dukes of Hazzard. Okay, can't watch it on TV anymore. But every time this car, in this show, there was this family of moonshiners. That's people who illegally make liquor and sell it without being taxed. Okay, and they would always be chased by these relatively incompetent sheriffs from the county that they lived in. Now, for whatever reason, this county didn't see fit to spend money building bridges across rivers and lakes and swamps and stuff. They just built ramps. And during all of these car chases, this orange 69 Charger, which is a great car, would jump over things. And it was always practically filmed. Right? So we're talking like an actual car was jumped over all kinds of things, actually, okay, in the show. Just jumped over whatever. Okay? Whatever they felt like jumping over, they jumped the car over it. But always the car followed a proper projectile arc. Okay? So I'm going to show you a quick video clip here of this particular jump, and then we'll solve the problem on it. Okay, so I want you to copy this example down. We're going to use it to review what we talked about last week with the mega whoosh slide and all of that. Okay, so the General Lee is jumping over the riverbed. This is the information we know. The speed of the General Lee is 32 meters per second upon launch. Okay, and the ramp is angled at 20 degrees above the horizontal. Right? We want to find the distance across the river and the maximum height of the General Lee. It's okay if you're not done, guys, because we're just going to kind of use it for review here. Okay, so this is what we got. The General Lee is taking off, okay, along this vector. The magnitude of this vector is 32 meters per second. The direction of this vector is 20 degrees above the horizontal. Okay, now as we saw, the General Lee flies through the air in a perfect projectile arc, landing in a well-planned cloud of dust that hides the fact that that beautiful orange Charger was destroyed. Okay, in fact, that show destroyed so many 69 Chargers that in the latter seasons, they actually had to use Dodge Challengers and film from a different angle where they looked similar. Because they actually couldn't find any more Chargers to destroy. It's very sad if you like classic cars. Okay. All right, so this is what the General Lee does. It lands over here. Its launch point and its impact point are level. Okay. So we need to write down a few of our givens. Okay, so we're just going to split this up into vertical and horizontal arcs. Okay, I'm going to make the vertical stuff red, and I'm going to make the horizontal stuff green. Okay, all right, vertically speaking, I know the acceleration. Negative 9.81 meters per second squared. I have to make it negative here because the General Lee does change directions vertically. When it's first launched, it's moving upwards. When it hits the ground on the other side, it's moving downwards. So I have to make down negative. Okay? Here's the other thing. This vector here has both a vertical component and a horizontal component. The horizontal component is the horizontal velocity, which is constant, of the General Lee as it flies through the air. Okay? The vertical part is the initial vertical velocity, how fast the General Lee was moving up or down the moment it was launched, because obviously that number is going to change due to gravity. Okay? Now, if I know the hypotenuse in this angle, can I calculate the other two sides? Okay. Now, this is the triangle you have to know. Right? You have to understand that this side is always going to be VI, this side is always going to be V horizontal. Okay? So I can calculate VI. Okay? VI is going to be the sine of 20 degrees times 32 meters per second. All right, so the initial vertical velocity is 10.94 meters per second up. Since the launch point and the impact point are level, what do we know about VI and VF? They're equal, okay? Because from a vertical perspective, all the car does is go up and slow down, slow down, slow down, and stop, and then come back down to the earth, okay? Since those two motions are mirror images of each other due to a constant negative 9.81 meter per second squared acceleration, okay, we know that when it comes back to the ground, it has to be going vertically the same speed it was launched at, okay? So I know then that VF is negative 10.94 meters per second. All done? Okay. Yep. Okay, now I can also calculate the horizontal component of that velocity because I can calculate the x component of this. Okay, so V horizontal is going to be the cos of 20 times 32, looking for the adjacent side this time. Ooh, cos of 20. All right, so 30.07 meters per second. Now I'm keeping all my decimals for significant digits in the calculator. Okay, if we want to calculate how far it goes horizontally, what do I need? I need time. You almost always have to calculate time regardless of what type of projectile motion question you have. You do. You almost always have to get it. Okay? It's so rare that you get a question where it's given to you. Okay? It's the one thing that applies to both. So, looking at my vertical information, I'm pretty sure I can calculate time with these three things. And I'm just going to use this formula. A equals VF minus VI over T, right? I have VF, I have VI, I have A, so I should be able to calculate T. So I'm just going to manipulate for T. Okay, that's going to be VF, negative 10.94, minus VI, 10.94. And then I'm going to divide that by negative 9.81 meters per second squared. Okay, so if I go negative, and then I go this number, and then I subtract that number again, okay, I get that, and then I divide that by negative 9.81. That seems about right. I mean, I know they paused it in the middle and they slow motioned it and all of that, but yeah, it would have been flying through the air for a little over 2 seconds. Okay, it's a pretty good hang time for a car. Okay, 2.2 meters per second. Or sorry, 2.2 seconds, sorry, not meters per second. All right, that number can come over here and be used because the time is the same for both. Okay, D equals V times T. 30.07 times 2.2 seconds. Okay, and of course I'm going to keep all the decimals here. So, oops, that number there, times that number there. Whoop, forgot to put the times in. All right, so it's 67 meters across that river. To put that into perspective, that's the distance from the starting line on the track over there to probably about 10 meters past where the gate is on the track. Actually 15 meters past where the gate is going onto the track. Is that a long way for a car to fly? Don't try and fly your car that far. Okay? Not only will the car be destroyed, you will with it. Okay? They had actual stunt drivers in those cars, believe it or not. Okay? None of that was done by remote control. If you ever become a stunt driver, piece of advice. Hold the steering wheel like this, with your thumb on top of the steering wheel. Do not put your thumb under the steering wheel. Why? When you hit the ground, you will go forwards and you will snap and dislocate your thumbs. Don't hold the steering wheel with your thumb underneath as a stunt driver. You'll dislocate your thumbs. Probably that's the least of the injuries you'll sustain, but you know, it's a hard life being a stunt driver. Okay. That's only part of the question. What was the other thing the question wanted us to calculate?
Your highest distance.
Maximum height that generally attains above the ground. So we know this number is 67 meters. Okay. Now we need to calculate the height. So we got to go back to our diagram here. The maximum height of the generally occurs here in the middle of the jump. All right. So how much of the time has passed when it gets to there? Half. Okay. So I have to remember that this time I calculated, I got to use only half of that time. Or the other thing I've got to remember, okay, about this point is that the vertical velocity at that point is 0, because that's the maximum height. So from a vertical perspective, it's been going up, 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 but ever slower, and then for in that instant there, it stops before falling back down. Thank you, Mother. And so VF is 0 there. All right, so this is changing now. I'm not going to use this number. I'm going to use that number, okay? And the time is changing from 2.2 to half of that. I have two choices here. I'm trying to find D. There are two formulas I could use that would get me D from the information that I have. This one. Okay, I have VI, I have T, and I have A. So I could use that formula. I just have to remember to use how much time? Half, not 2.2 seconds. Okay, my other option is this one. Okay, I'm looking for D, I have A, and I have both speeds. So I could use that formula as well. Choice is yours. Okay, the advantage of this formula is you don't have to manipulate the formula. The disadvantage of that formula is you have to remember to use half the time, and that's what people forget. Okay, the disadvantage of this formula is you have to manipulate it. The advantage of this formula is you don't have to change any of the numbers. You can just use the numbers they were given. Okay, either way will work. All right, and I'll prove it to you here in just a sec. First, let's do this method here. All right, so I have VI. Okay, so if I'm doing that one there, I'm going to go 10.94, okay, times 1.1. I'm just going to write 1.1 in there. Okay, plus 1/2 times negative 9.81 times 1.1 squared. Okay, so I'm actually going to take that time number and I'm actually going to divide it by 2, so I have a real number to use there. All right, divided by 2. All right, so VI was 10.94. I got to go up a ways to get that. There it is. Okay. Times plus 0.5 times negative 9.81 times that number squared. Okay, so the generally is going to be 6.1 meters above the ground. That's over 20 feet. So imagine dropping a car from a height that's greater than 2 basketball nets would be. Okay, that's essentially what's happening, just from a vertical perspective, okay, to this car. Now, the other way we said we could do this was to use this formula here. We would just have to manipulate it, okay, for D. So that would be VF squared minus VI squared over 2D. Sorry, 2A, sorry. Gives us D. Now, VF is 0, so I can cancel that out. So what I'm going to have is 0 squared minus 10.94 squared divided by 2 times negative 9.81. All right, so 0 minus the 10.94, which is way up here, squared, okay, divided by 2 times negative 9.81. Ah, look at that. It's exact't the same number. Makes no difference which way you do it. Okay? Either one will work just fine. All right, questions on that? That is an incredibly typical, slash I totally put that on an exam, type of projectile motion question. Okay, this is basically the same question. It's not a car, it's a cannonball. Right? See if you guys can solve it. You can look back at the last example and see what you did in the last example. Okay, so I'm going to give you a few minutes to work on that and see how you do with it. All right, so we got a cannonball, okay, and it's fired 40 degrees above the horizontal, okay, at 140 meters per second. Okay, so that's how this thing starts out. We know it's going to follow this arc. Okay, we're going to assume, because we're not told otherwise, that its impact point and launch point are equally high. Okay, they're the same, they're level. All right, so knowing that, okay, we move forward to our vertical givens and our horizontal givens. Okay, so we have to remember that this side of the triangle is v horizontal and that that is constant, and that this side of the triangle is the initial vertical velocity, which will change. Okay, I'll take those guys. Okay, so if I'm going to do some vertical stuff here, okay, A is going to be negative 9.81 meters per second squared. Okay, VI is going to be the sine of 40 degrees times 140 meters per second. Okay, so 89.99 meters per second, and that's positive. So what's VF? Negative 89.99 meters per second. All right, over to the horizontal stuff. V horizontal, okay, is the adjacent side, so cos of 40 times 140. Okay, so that's going to be 107.25. Okay, I'm trying to find the horizontal displacement first. What do I need? Okay. What do I need for that? I need the time. Okay, I can find that with my vertical information. Okay, so T is going to be VF minus VI over A. So that'll be negative 89 minus 89, obviously with all the decimals in there, divided by negative 9.81. Negative that number. A minus that number. A divided by negative 9.1. Okay, so that cannonball is in the air for 18.3 seconds. That's quite a while. Okay, 18.3 seconds. All right, that number can come over here, 18.3 seconds, and now I can calculate D, V times T. So I take my 107 and multiply it by the time. Oh, sorry, I put the negatives. That should be positive, guys. I messed up where I put the negative there. I'm just going to take that negative out because I messed up there. Whoa, where did I get that 1.87? Oh, I hit enter again. Okay, sorry guys, I messed up here. Again, the struggle is real because it feels like Monday even though it's not. 18.3 seconds. There we go. Okay. Is that a long way? Yeah, we only have, I think, 2 significant digits in that question. So according to our 2 significant digits, this thing flies 2 kilometers. Okay. You could easily make a cannonball fly 2 kilometers. Artillery shells can fly 100 kilometers or so. Okay. So we can make those go a long way. Okay. 2.0 times 10 to the 3 meters. All right, what was the other thing I wanted to know? What was the other thing we had to calculate, guys? Okay.
Maximum height.
Maximum height. All right, so go back to my diagram, okay, and I modify it, right, so that I'm looking for the maximum vertical displacement, which occurs halfway through, where VF equals 0, okay, and I'm just going to do it one way, okay, the way I like, VF squared minus VI squared over 2A equals D. All right, so that's going to be 0 minus squared and divided by negative 9.81. Okay, is that pretty high? 8.3 times 10 to the 2 meters, 830 meters is the maximum vertical height of the cannonball. Okay, that's pretty high. Oh, whoops, yes. Sorry, guys. Man, I gotta go back to bed and start over. This number, I forgot to put the 2 in there. That's better. 400 meters. Okay, 4.1 times 10 to the 2. Okay, everybody all right with that? Okay, pretty much the same as the general E question. Okay, pretty much the same as one of the questions on your unit exam. Yep. All right, let's look at an example of bad movie physics down before. Okay, still projected at an angle question, but it gives you different information this time. Okay, I actually give you the time in this one, and it's a lot less work than the other ones we've done, provided you figure out what little trick I've given you. Okay, so we're looking for the angle at which the rock or ball is thrown. Okay. Okay, so ball's thrown into the air at a velocity of 35 meters per second, so it's like this. Okay, but we don't know what the angle is. So I don't even know if I've drawn that even remotely close to what it should look like. Right? What we do know is that it's in the air for 2.5 seconds and lands 70 meters from the point at which it was thrown. So there's the arc. Okay, I know that this distance here, the horizontal distance, is 70 meters, and it's in the air for 2.5 seconds. So what can I calculate with those two numbers? Exactly. I can calculate the horizontal speed. Right? Now, even if at this point you don't know why you want to calculate that, it's something you can calculate, so calculate it. Okay? So we're going to go V horizontal equals D over T, and that's going to be 70 divided by 2.5 seconds. Nice. 70 divided by 2.5. All right, so that's 28 meters per second. Here's how that helps me. I now know one of the two sides, or another side of that triangle. Would you agree? Right? We know that V horizontal is the adjacent side of that triangle to the angle. Well, since I know the adjacent side and the hypotenuse, can I figure out the angle it was thrown at? What trig function should I use here? Cos. Yeah, because I know the adjacent side and I know the hypotenuse. Right? So I can find theta by going inverse cos of the adjacent side, 28, over the hypotenuse, 35. Okay, so it's thrown at 37 degrees above the horizontal. All right, now that question, did that require as much work as the others? But did it require you to think a little more? Sometimes I give you questions like that. Okay, good work today, guys. We'll leave it there. We'll go over your acceleration lab, start a class tomorrow. It may be later tonight before I get the mark, okay? But definitely you'll have your marks tomorrow, okay? We'll go over them in class.